depending on where you are. Today, we're honored to have two presentations on storage. Our first presentation will be Energy Storage Value Streams in DERCAM by Nicholas DeForest. And then our second one will be by Alasdair Crawford from Pacific Northwest National Lab. So I will turn it over to Nicholas and encourage people to put any questions in the chat, and we'll go from here. So Nicholas.
Thank you. Yeah, and thanks everyone for being here. I have a pretty high-level talk today discussing potential value streams for energy storage, particularly in the context of a modeling tool like DERCAM, but I think some of the ideas here can be applied generically to energy modeling and energy analysis. So just quickly, the items I'd like to go over today, just a quick overview of what DERCAM, the tool, is. We did a presentation last year that I think was recorded, so if you haven't seen that and you're interested to learn more, that webinar might be a good place to start. But I think if you have any questions about how DERCAM might be applied to your analysis of projects, feel free to reach out to me directly. I'd like to also talk about the approach that we use within DERCAM to assess the value of energy storage, or really generically any distributed energy resource. And I should say DERCAM is primarily focused on optimizing or analyzing from the utility customer point of view, or the microgrid point of view. I think there's additional values and applications of DERs in storage under different sort of ownership paradigms or different operation paradigms that maybe aren't covered here, that might have some relevance to what DERCAM does or might not. But again, if there's questions about that, feel free to reach out. I also want to highlight some of the, in discussing these value streams, limitations that the approach that DERCAM uses kind of imposes versus other approaches to this type of problem, primarily those that are simulation-based rather than optimization-based. And then going through each value stream, thinking about how they're captured or what types of additional definitions or characterizations that users need to make in order to capture those, and some limitations that our approach introduces. And then finally, just highlighting some of the resources that are not presently available yet, but are items that we're working to produce under this project, and I think will be available in the near future if you'd like to try some of these things out for yourself. So just as a reminder, DERCAM is an optimization problem, and we like to think of it as this big holistic problem where users are able to define all of their inputs in terms of, their energy purchasing landscape, prices, rate structures, other incentives and opportunities, their site characteristics around load and the availability of solar or other resources that might power different DERs, the characteristics of those DERs themselves, how they perform and how much they cost. And then if you're doing a detailed multi-node microgrid, how the network is configured. Users are then able to sort of define what their objectives are. Is this purely a cost optimization? Are they doing resilience or reliability criteria or other things? And then taking all those things into account simultaneously, DERCAM is able to come up with a solution that both sizes the different resources, including energy storage in this case, but also gives some indication for where they're placed and how they're used in order to maximize the objective that the user has defined. So thinking about in the context of the very prolonged process of designing and building out a behind-the-meter energy system or energy storage application, I think DERCAM is primarily useful in the early stage. It's a way for you to develop a understanding of the feasibility of pursuing different value streams or utilizing different technologies, and understanding what are the sort of key drivers to success or failure or feasibility within your project. So we like to think of it as this exploratory design tool where users can play around with it, get a sense of their project, what matters, what doesn't, iterate through that a bit as the data gets a little more refined, and then it sort of gets passed down the line to additional, more detailed modeling and design work that needs to happen for the project to actually be actionable. It also gives you some insights into processes further down the line, thinking about utility approval. So if you understand how your system, how your battery system or your behind the meter system is interacting with the grid, interpreting and exporting power, et cetera. Financing, because you get a sense of all these economic metrics of performance and the value streams captured, and then operation, like how you expect the system to actually be used. So the focus here is on energy storage, but like I said, these value streams that we're thinking about within DERCAM kind of apply generically to any investment that you might make. And just as a refresher, these are sort of a list of all the technologies that we currently consider within DERCAM, and users can easily select amongst these, and the model will automatically consider competing and complementing strategies for pursuing whatever objective between these different technologies. And then again, just for detail, some of the advanced features that DERCAM has that kind of distinguish it from other modeling tools within this space are the ability to create this sort of multi-node internal microgrid network, which changes the dynamic a little bit if you have to consider power flow within your network for the siting or sizing of DER assets, including storage. And then again, we have a public version of this tool available as a desktop UI application. There's some limitations to using this presently. We have a project ongoing right now where we're modernizing this as a browser-based tool, which I think is expected to be released sometime over the summer, at least in beta. So if you're interested in trying this out for yourself, you can go to our website and explore the old application, which you see here, or if you want to wait, if you sign up, you'll be on our mailing list, and we'll let you know when the new version is available to play around with. So this is a simple diagram that kind of illustrates the approach to understanding the value of any DER asset within DERCAM. Typically, the whether to invest and the capacity to invest is a decision variable that the optimization is going to be selecting based on your objective. And then within that capacity, the model will essentially select a portion of it that will be used for active dispatch. So that's basically, charging and discharging of a battery to pursue certain objectives. But it might also, depending on how you have, your different value stream inputs configured, capacity reserved to pursue these other value streams. And then with that capacity selected, then you can see like how it's actually utilized to capture value. And so you get what we call a sort of stacked value approach. So you're simultaneously pursuing all these different opportunities in order to maximize this bar on the right. So you might think about, oops. So I didn't realize I had transitions in there. So you might think about, reducing energy costs, reducing demand charges, and getting revenue from exporting locally generated electricity or participating in grid service markets. And this DERCAM approach allows you in one optimization to essentially explore all of those simultaneously and sort of maximize the value. So let me just click through these. I didn't realize transitions here, but so just quickly, I want to highlight some of the benefits and limitations of doing this DERCAM optimization approach. So like I said, you're able to, within one optimization, select or find the optimal value for all of these different decision variables holistically. So we're not having to explore separate scenarios where we, do and do not pursue, different value streams. All of that decision making is done for us. And that really simplifies the process, especially in the early stage of looking at a diverse set of value streams that may compete with one another or may complement one another depending on how they actually influence the sizing decisions and the operation decisions. But because, optimization, you need to have a problem that's practically solvable. You have to give up some detail in terms of the time granularity, in terms of the time horizon. Within DIRCAM, we're sort of simplifying our time horizon down to a kind of representative year, and then that year is itself represented by a subset of design days. So we're not doing a full like 8760 annual exploration that you can easily do in simulation tools like Homer. But to contrast, for simulations, oftentimes you'll have to make some decisions in advance of your simulation that are grounded on assumptions or require multiple iterations of analysis in order to find the right solution. I think a good example of that is if you're doing demand management, demand charge management, and you need to figure out like what's the level of demand charge that I'm targeting with my storage charging and discharging. Oftentimes you'll have to select for or give bounds on that, and then develop the simulation, the optimization, or excuse me, the operation strategy as a result. But that initial selection might not have been optimal, and then every decision subsequently is sort of influenced by that. So like in the second point, oftentimes you'll need to iterate a lot in order to converge on the best solution. But like I said, you're able to explore in more detail the sort of time horizon that you're looking at, and in particular get into some of these corner cases of like, well, what happens if this type of event coincides with this type of weather or this type of load? So there's definitely a benefit there. I think these are often complementary approaches where optimization might be a good place to start to get an idea of feasibility, and then simulation is a good way to validate those results. But I guess it depends on what your sort of project objectives are. Excuse me. So quickly, these are high level the value streams that we're looking at pursuing within DIRCAM. Energy costs, demand management, which is a big one for behind the meter systems, short-term reliability, longer-term resilience to outage, and then pursuing sort of revenue opportunities from demand response and ancillary service programs or markets. Sorry, again, didn't realize I had transitions here. So for energy costs, there's lots of ways to do that. If you have a time of use tariff, then reducing your on-peak consumption can be a driver. If you're under a real-time rate or in a wholesale market, then avoiding periods where prices spike can be a good way to reduce costs with storage, energy costs for storage. And then in some applications, there's these sort of critical peak programs where in advance that the price of energy is going to go up quite a bit during a set period of time, and storage can be a really effective way of mitigating the costs related to that. Self-consumption of PV is a big one if you have a suboptimal export rate. So if you're not getting a good rate or you're not able to sell PV back to the grid, then PV plus storage, that's going to be a big driver for value. Energy arbitrage is another one, but honestly, in my experience, which is mostly in the US under retail rates, the price arbitrage opportunities under retail rates is never really strong enough to drive storage adoption or use. And then again, you can use storage in some situations to increase the value you get out of exporting electricity, for example, from PV generation. So all of these values are sort of implicitly captured in the work, the DIRCAM optimization. The dispatch strategy that you get out of the tool implicitly captures all of this because it influences the net importing or exporting of power within your system. So there's really nothing that needs to be done from a modeling standpoint in order to make sure these are captured. Similarly for demand management. So there's lots of ways that the magnitude of your demand for importing or exporting can influence the cost of your system. And so having storage available to flatten those demand spikes is often, at least in the US context, a big driver of the value of storage technologies. And I think increasingly with the proliferation of EV charging and especially fast charging, having stationary storage that's able to mitigate those demand spikes is another thing that can be a big driver of the value of storage. I think I've heard a lot about especially EV bus fleets, their sort of charging stations, having stationary storage there in order to mitigate the demand profile from fast charging buses is a big up and coming application there. And then again, if you have other technologies that are intermittent, like wind or solar, if you have sudden drops, like short-term drops in the output of those systems, having energy storage present to sort of buffer those can be a big driver of value. And like energy, the energy cost value streams, these are again implicitly captured within the model. You know, we're dispatching the technology and influencing the net importing, and that's gonna capture this here. Reliability, which in DERCAM we think of as more of a short-term event, is one thing that we're able to capture somewhat simply within DERCAM, but you know, in instances where very short-term interruptions to power quality disruptions might have significant impacts on operations, like causing machinery to trip off, can be extremely costly, especially in industrial applications. And so we want to capture the value, the potential value of that, usually through thinking about a value of lost load metric. So if you understand within your project context what's the actual cost of going down, you can very easily capture the value of short-term reliability. And this, unlike the other ones, this one requires essentially reserving storage capacity in order to ensure that you have adequate energy and storage to meet the requirements of your site when the event occurs. This is, like I said, this is pretty simple within DERCAM because of our lower time granularity. We can't capture, you know, very short-term fluctuations in power quality. And so this is just, you know, if you're able to define these value of lost loads, you have an understanding of what the historic reliability of your site is, you can plug in those data and get a sense of, you know, what's the potential value of having storage within there. Resilience, we're thinking of like longer term outages. So if the grid goes down for, you know, multiple hours or multiple days, what's the value of having resilience there? So within DERCAM, we're able to explicitly model these outage situations. We can model a day or multiple days where the grid is not available and you need to meet your energy requirements. And actually, you know, how are the different DER assets allocated and dispatched in order to ensure that that happens? You can specify within those days what level of your blue sky load needs to be served and what portion of that load might be sheddable. If there's costs associated with not serving some of that non-critical load, all of that can be implemented, and that sort of indicates what the financial value of that resilience tends to be. Again, there's a huge variability in what value of lost load might look like in these different circumstances. We're doing work now with municipalities within the US that are looking at prolonged outage, so providing sort of resilient islands within communities where prolonged outage might occur, for instance, in the event of hurricanes. And quantifying the value of a service like that, sort of critical life-saving services, is difficult because obviously that's very, very valuable. But you know, all those things can kind of be captured within the model. So then finally, we have these revenue opportunities that storage might be good for. And again, these are very US specific, but the tool itself is pretty generic in terms of what's needed. There's input tables that allow users to define the prices related to offering these services into a market, and also the requirements for how they are, how they're expected to be utilized. But again, I think the simplifications in the time granularity of DERCAM make this aspect of it a bit of a challenge. I think, you know, for market prices for some of these products vary quite a bit, and the value comes not in, you know, necessarily being in the market day in, day out, but being able to capture those periods of time where the prices spike for whatever reason. And so, you know, you can capture a little bit of what the potential value from these might be for a storage application, but there's some simplifications. And you know, I think this aspect of DERCAM typically requires a fair amount of iterative modeling to ensure that the solution that you're getting is reasonable given all the assumptions. And again, so DERCAM is essentially reserving capacity of storage in order to ensure that there's capacity available for when the program that you're participating actually exercises the resource. There's a lot of uncertainty around if you're in these markets, when and how is your resource going to be exercised. And so there's a lot of simplifications that subsequently have to be imposed there. So finally, there's a question of battery degradation. So if you're using storage to do any or all of these, that's going to impact how your storage is charged and discharged, and what sort of state of charge it tends to stay at any given period of time, which all is going to affect the degradation of the storage capacity. And we're not explicitly capturing a lot of that given the simplifications. We're allowing users to specify the replacement costs and lifetime of storage assets within the model. But that, again, that's an assumption that they're making in advance, and they don't necessarily know how the outcome of the optimization is going to potentially reduce the lifetime of that asset. So this, requires a little bit of iteration, or may require users to be conservative about the lifetime of their asset initially, in order to prevent the model from overestimating the value of that asset. And we also, because we're operating within a sort of prototypical design year approach, we don't capture sort of year-to-year capacity loss in operation. So if you still have with a battery that's lost capacity but is still within its sort of usable life, the value is obviously going to be reduced in subsequent years as that capacity diminishes. But we don't capture that in the public version of DERCAM. We do have a multi-year version that's sort of a research tool, but as you might expect, if you're modeling multiple years of operation within an optimization context, the computational resources needed to solve that model go up quite a bit. So that's not something that's available to the public right now. And we do also, so we did work on a battery degradation model within DERCAM, where users can specify the lifetime, the target lifetime that they require for their battery, and the model then limits the use of that battery in order to ensure that that lifetime requirement is met. But the problem there is, at least as it's currently configured, is this is a very conservative model, and it tends to reduce significantly the value that you're able to capture with storage. So it basically, reduces the value of storage, reduces its use, like the frequency of charging and discharging, the depth of discharge, et cetera. And this model is also really chemistry dependent. So I think it's based on a certain lithium chemistry right now, and it has a lot of internal parameters for configuring that. So as different battery chemistries become available, it's going to be difficult to ensure that this battery degradation model stays up to date with all of those. But so this is just something to consider. Without consideration of degradation, the model might be overestimating the value of storage in all of these value streams. So I'm coming up on 25 minutes. So I just want to quickly say the deliverables that we're sort of producing under this project are sort of prototype models within DERCAM that capture these different value streams. These are things that we want to make available to users of DERCAM. So if you're interested in exploring an analysis that captures some or all of these, we want to make sure that there's a resource for you to grab and immediately get started, in addition to providing documentation for how to use DERCAM in general, but also how to use these specific models. And then we're also developing at sort of an earlier stage a generic microgrid control software that uses optimization for the dispatch of these technologies. And so we want to make available these use case models within that control framework that simulates the operation of a system pursuing these different value streams. And I think once our work on this project is concluded, these types of resources, I think, will be available somewhere on our website as just a sort of a standing resource for folks to use. So with that, I'm done. I think if you want to learn more about the DIRCam tool, you can simply go to dircam.lbnl.gov. There's a sign-up link there if you want to actually use the web tool itself. You can sign up for an account, and then if you do that, you'll be on our mailing list, and you'll find out about any new releases or new things. And then if you have specific questions, you can email dircam@lbnl.gov, or you can email me directly. I'm happy to chat with anyone who has more detailed questions about the tool. So with that, thank you so much for your attention. I'm happy to take any questions.
Yeah, thanks, Nicholas.
Thanks. I'm looking now at the chat so I can see if there are any relevant questions there.
Yeah, sorry about that. Yes, so thanks, Nicholas. And there's a question in the chat, but why don't we go with Alasdair, and then we'll go open up kind of the Q&A.
Okay, sounds good. Let me stop sharing.
All right.
Yeah, you did. You already stopped the share.
Alasdair,
hello.
can you share?
Yep. I'm sharing my
Here
screen
we
now.
go.
If everybody can see it.
Great.
All right. If everybody can see this, and can everybody hear me? Okay.
Yes, thank you.
Okay. Cool. Hi. Hello, everyone. Good morning or good evening. My name is Alasdair Crawford. I'm a computational scientist at Pacific Northwest National Lab, and we're going to go over some of PNNL's battery modeling and degradation at the battery energy storage level, the system level. Oops, sorry. So I quickly going to acknowledge other members on the team for UI Assist. So that'd be Vish Vanathan, who's a senior chemical engineer, and Vince Renkel, who's our advisor. So we're going to go through performance modeling of battery energy storage systems. How we do this is based on time series data sets from testing and actual operation of BESSs on the grid. How we can take those models from real data and scale them to be applied to other systems, and how we can do some safe health modeling, taking insights from modeling on the single cell level to the system level. Yeah, so here's a quick overview of the data sets that we have to work with. So at this point, we haven't actually counted these. It looks like we've got 9 data sets to work with of these various systems of different chemistries, with kind of a fairly widespread of energy to power ratios. They're all kind of at the megawatt hour scale. So for each of these, we generally have about 1 to 2 years of operational data. The WACEF here is Washington Clean Energy Fund. So there we had a collaboration with utilities in Washington State where they got some funding for putting batteries on the grid, and in exchange, PNNL would analyze them. And we also have a collaboration with EPRI, so they've provided us with some other data sets that we can work with. And these 2 red ones are kind of hot off the presses. We just finished testing these 2 at the bottom. So they're not part of this analysis in this presentation yet, but over the next few months, they'll be incorporated as well. Yeah, so from the Washington Clean Energy Fund systems that we analyzed, so these are the kind of descriptive metrics that we analyzed on them. Just going to give you an overview of, we're looking at the discharge energy, we're looking at the ground trip efficiencies with or without auxiliary, stuff like that. But that's not really that useful for modeling, except as a check. So what we do is we build a performance model, and what we're calling a performance model here is how the vendor-defined SOC changes over time. So that's the y-axis here, versus the SOC in the x-axis here. And these different colors are different different powers, with negative being charge, positive being discharge. Because basically the philosophy here is you don't need to make any assumptions about how the defender is defining the state of charge. If you just look at how the defender defined state of charge changes based on the power and state of charge. And that allows you to do long-term economic modeling of the batteries. You know that the powers available to it are those that keep the state of charge within a certain range. So a basic model setup is just going to be that the rate of state of charge change is going to be proportional to it's not proportional, it's going to be a function of the power and the state of charge. For a basic linear model, which is equivalent to like a constant efficiency model, the rate of change of SOC is just linear with the battery power, with different coefficients for charge and discharge. For a nonlinear model, there's more terms based on the power and the SOC and their interactions. So what you see on the right here is for a vanadium flow battery. So those have much more dependence of the performance based on the state of charge. There's a lot of variance here. That's less the case with lithium ion systems. So in general, if a battery has a better performance, it's going to charge faster and discharge slower. That is, the state of charge will decline less during charge and increase more during charge. So basically up is good here. So to validate it, what we do is we take our entire data sets and we split it up into charge and discharge cycles. We loop through every single cycle, and for each one, as you can see down below, we build the data on all the previous cycles, and we use it to predict how the SOC changes during that cycle, so that we're testing the model's ability to predict performance. There's some model parameters that we need to tune, and the way we do that is by minimizing our out of sample error, basically. So we'll get into that a bit, but so we use this approach to basically ensure that we're really testing the model's predictive abilities, and we're not making it either too simple or too complex, both of which will hurt its ability to predict. And especially as we get the model more complicated with stuff like taking degradation effects into account and such, it's very important to have a good validation to make sure that these upgrades to the model actually make it better at predicting what will happen. So here's some validation results. We are using the Alasdair net algorithm, which basically does some automatic feature selection for us. So that's good for being able to look at complicated interactions while avoiding making the model too complicated and overfitting. So these plots on the right here are the out of sample error for 7 of these systems where we're building models, and the x-axis here is number of days of testing. So we can one thing this shows isn't just comparing models. For example, like here, the red is the more complicated Alasdair net nonlinear model, and the blue is a simple linear model, which is equivalent to constant efficiency. But by plotting it this way, we can also see how much data the model requires to start converging, and that gives you some information on how many days of testing you need to have a good characterization of the battery's performance, and where you start getting diminishing returns. So in general, this approach by using Alasdair nets and some nonlinear terms works pretty well across the board. decreases the battery error, sorry, the out-of-sample error of the model some more than others. For lithium-ion systems, it makes a smaller difference in general because, like I said previously, lithium-ion systems have more consistent approaches. There's big differences for flow systems because like I said, the flow systems have a lot of variance of the performance based on their state of charge. Yeah, so we have a scaling approach here as well, so we can take up this model and slap it down to another site to analyze what might happen to try and predict economic valuation. So we have a pretty simple procedure for this. What we do is when we're building a model, we take the power of the battery at each step and divide by the rated energy, which gives us a normalized power. So then we just built the model while using this normalized power as input rather than the power. So when we want to look at a new system, we just multiply the new rated energy back in. So we can build a model on a system with a given nameplate energy and scale it to another nameplate energy. So to try and validate our approach, we took from our data sets, we took 3 data sets where the lithium ion system is nickel based, so NCA or NMC, and we took the 6 possible pair ups and used data from one system to apply a model to system B, and then compared it to the results of if you generated a model during testing that's improved over time. So yeah, so all these 3 different energy storage systems have different rated power and energy, but the same lithium-ion nickel-based chemistry. Here in each of these, the flat line is the modeling error from using the scaled model from the other system, while the line that changes over time is from building a model over time. So you can see that for each of these, the scale model always does better at first because it takes some time to build a model for each system. And the crossover point gives you some information on how much testing you'll need to do better than a scaled model that has the advantage of more data from the original system. Yeah, so for some of these, even the updated model doesn't even touch the scale model line. So it over the course of testing, it never actually did any better. So this tells us that the scaling approach does work quite well for taking models from existing systems and applying it to a new system where you might know about it is the chemistry and the rated energy. So because that's the question you kind of have if you're doing a scale model, right? Which is like, oh, well, how much of this information, how much of this model is specific to this system, and how can we apply it to a new system? And it looks like the answer is quite well. We'll now that we have some more data sets in, we'll expand this for more combinations and see if that holds up. Okay, so incorporating state of health. So you want to incorporate state of health in models, especially if you're looking at kind of like a multi-year economic evaluation. Sometimes operating the battery might give you like short-term economic benefits, but by reducing the battery's lifespan, you've lost money, and you don't want your model to do that, right? Or you don't want your model to encourage you to operate the battery in a way that loses you money rather than gaining you money, right? So to model this, we adjust the model. So the rate of change of SOC also depends on this degradation term D, which takes the battery's history into account. So over time, as the battery degrades, we expect its performance to change, so its rate of change of SOC to change. In general, if it's related to capacity fade, we would expect the state of charge to change faster for both charge and discharge. if it's due to internal resistance change, we expect it to discharge faster for a given power and charge slower for a given power as it degrades. So those two phenomena are kind of in different directions. So we end up having this degradation term affect the charge and discharge differently because of that. And that also gives us some insight into how much of the degradation is due to capacity fade versus internal resistance. So I'll get into that in the next few slides. This degradation term itself, we want to be a function of power and SOC. So this is going to focus on lithium ion degradation, where we have some fairly decent idea of the mechanisms responsible for the degradation. So we can kind of model that effectively. For lithium ion, especially the parasitic reactions that are responsible for capacity fade are very vary a lot with state of charge. At high state of charges, most of the reactions that you don't want to happen a lot faster. So this slide just kind of goes over some of the degradation mechanisms. So the primary one that we care about is this SEI solid electrolyte interface layer reaction. So between the electrolyte and the graphite in the anode, we have this SEI layer that forms. It consumes lithium in a parasitic reaction. So we both lose lithium to this SEI layer, and we also have an increased internal resistance. We have some other interactions here, like as the SEI layer gets thicker, that this rate slows down. So that's something that can be modeled. We also have the graphite expands and contracts, or charging discharging, which cracks the SEI layer, and new SEI can form quite quickly in the cracks. Also, nickel in the cathode can dissolve, which reduces capacity, but it could also find its way over to the anode and speed up this reaction. We've done some physics-based modeling. We've got a paper published in the journal Power Sources where we use this pseudo 2D model using COMSOL for finite element analysis. We also modeled heat generation. But this on the right is how we ended up setting up the model, where we have one dimension along the length of the battery, kind of split up into anode, separator, and cathode, and our other dimension is along the particle radius, so we can calculate the concentration along each point along it. This sort of modeling doesn't explicitly get used for the system level modeling, right? It would be too complicated, but we were going to use this to generate insights to help us build a empirical statistics-based model for the storage at the storage level. So here's some results from our from our in-house data, where we've got these 4 types of cells that we cycled at different depths of discharges. Here the points are what we measured for the capacity loss, and the line is the model. So this is just to kind of show that we've kind of got a handle on modeling it for all different chemistries. And so from that model, we can end up looking at the degradation rate as a function of the power and the state of charge. So we can use this to generate terms in the performance model. So what this is in this graph is basically the rate of SEI layer formation as a function of power and state of charge. There's some missing pieces. So this doesn't take into account that as the SEI layer grows, there's a diffusion limitation which slows down the growth. So in a perfect model, we'd want to have degradation as a function of state of charge, power, and the state of health. So the rate at which it degrades due to SEI layer formation should slow down as more SEI layer forms. but we're not taking that into account just yet. Yeah, so from this, you can also see that kind of as expected from the chemistry, the rate to degradation is approximately exponential with the state of charge, and it increases with increasing power, whether it's charge or discharge, but the effect is bigger for discharge. Sorry, charge. Right, so for actually applying this on the BES level, we start with a simple linear model for the performance. So here we've got the rate of the rate at which state of charge changes is a constant, which is just self-discharge, plus a constant times the power discharged, plus a constant times the power charged. So it turns out these coefficients are equal to 1 over the discharge energy capacity and 1 over the charge energy capacity. So that gives us some idea for how we can interact that with the state of health. We have the state of health affects the charge and discharge capacity. So in the next equation, we've added a state of health interaction term. So yeah, like I said previously, here it's affecting the charge and discharge differently, because again, these reactions decrease the capacity but increase the internal resistance, which have different effects on charge and discharge. We can also look at these coefficients related to the degradation and compare them. If they're very similar, then we've got the primary mechanism is capacity fade. If they're very different, then it's internal resistance. So you can kind of look at those two magnitudes of these coefficients and have an idea of how much is due to each. So what for the latest model we've been using for the state of health model, we're having the degradation be proportional to the exponent of state of charge plus power squared, and that kind of takes into account roughly what's happening in our physical model. This state of charge plus power term is basically has to do with the chemical overpotential, and we know that the rate of SEI layer formation will be exponential with that. And this power square term has to do with the SEI layer cracking and new SEI layer forming in those cracks. Yeah, these coefficients A and B are determined by seeing what minimizes out of sample error, as discussed previously. This also has the advantage of this always being positive, so the battery always degrades. In the past, with approaches where we've had the degradation be proportional to the total amount of energy charged or discharged, we would sometimes end up with expressions that could go negative, which if we're feeding this to an economic optimizer, that could cause problems if it starts trying to exploit that, right? So we want to make sure that our function stays positive. Yeah, so here's some validation results. It's kind of a dense plot on the right, but here each row is different data sets we apply this to. The red is the degradation model, and the blue is just the linear model without degradation added to it. And we have here the y-axis is the in-sample mean error. And the reason we're doing that is because we want to know if it is overly optimistic or overly pessimistic about the battery's performance. So if it thinks the battery is doing better than expected, then it's going to be expected to be positive for discharge and negative for positive for charge and negative for discharge, because it's going to expect that the battery would charge more than it can or discharge more than it can, right? So we look at this trend where we don't take degradation into account the blue, and we see that it's overly pessimistic about how the battery performs at the start, and overly optimistic at the end, because it's not, and that tells us that it's not the not taking degradation into account is affecting it. We have this error that changes with time, going from too pessimistic to too optimistic. Here, where you have the red line with the degradation model, we see that it's pretty flat across the board. So that kind of tells us that it is taking into account how the battery performance changes over time pretty effectively. So kind of our conclusions and future work. So we've got a methodology developed and validated for predictive modeling of energy storage systems, including degradation and scaling. For our future work, we want to incorporate results from our new data sets. We want to improve our insights from and add more to the state of health model, because state of health modeling is quite tricky and could use more work. And we also have quite a lot of analysis on single cell data that we want to then bring over and transfer to the ESS level. So that's my 25 minutes. So thank you.
Great, thank you. So a lot of great information there on different opportunities for modeling on for both of our partners, and we appreciate the presentations by Nicholas and Alasdair. So there are a couple questions in the chat that maybe we want to start with, and then I want to open it up to see if people have additional questions. So why don't we start first with Nicholas, and does the DERCAM consider BESS battery energy storage system return on investment and its sensitivity to different applications? And then what are quantification methods applied over resilience around optimization during long-term planning analysis?
Sure, thanks. So in terms of the first question, yes. So DERCAM is optimizing the investments in batteries or other technologies, and it does that by it's optimizing the total annual energy cost. So that's sort of the objective of the optimization, and that takes into account all of the operating costs related to buying or selling energy or generating revenue, but also the levelized cost, capital costs for the different technologies and their operation and maintenance costs. So you can derive a return on investment or a net present value or a lot of additional metrics from what DERCAM is optimizing. But the objective is this total annual energy cost directly. I think there's some sensitivities to if you prefer to optimize based on a different metric, but that's currently what it does. We have some flexibility to define other objectives. And then in terms of quantification metrics applied over resilience, I don't know if that's thinking about like survivability metrics or things like that. We don't have those as inputs directly. What we do instead is users specify essentially the resilient performance that they require, and then DERCAM develops or designs the system to meet those. So that's typically done with defining when and how frequently the outages occur and what the critical load that must be supplied during the outage is. And then we've done, for DERCAM designs that have been produced using that method, then done a sort of simulation approach to actually apply them in a higher granularity environment to that outage scenario to get survivability metrics from that. But that's not something that's sort of natively part of DERCAM itself. It's all related, though, as what I would say.
Great. So thank you. So Alasdair, the state of charge variability has a large impact on performance model over multiple years. How does your study consider variability of state of charge, since it is driven by load supply gap with an example, more uncertainty?
Sure, yeah. I'm not sure if I entirely understand the question, to be honest.
Well,
but
yeah, Sanji may be able to ask it a different way.
So yeah,
If it,
thanks, Mark. So I think the question is about actually, so how does the SOC's variability generally, it all depends on the load supply curve. So that's how it drives the charge or discharge. So how does that will be considered in the degradation model? I mean, I know that you made it as a function of SOC, but do you assume like it's a fix, or how does the load and load variability taken into account when you are actually considering the SOCs?
so, I mean, basically how it works is that with the degradation model, it has the rate at which the SOC changes. That changes over time. So as the capacity fades, for instance, it's going to, the SOC is going to increase more during charge and decrease more during discharge because its capacity has gone down. So that's what the state of health model is attempting to capture, if that answers what you're getting at, yeah.
Yeah, thanks, Alasdair. Yeah.
Okay, yeah, sure, yeah.
So Subir, you had a question. What could be the possible reason behind using power in battery voltage varies with state of charge?
Yeah, sure. So that's because power is basically being used as a proxy for current. That I kind of assume you're referring to the equation where. Oh wait, okay, yeah. So we're looking at how the battery state of charge changes. So at higher power, the battery state of charge is going to change faster, but higher powers and slower at lower powers.
Yeah, so I was actually asking about the question like you mentioned. So you are supposed to use the current, and then if you use the current, then that can basically represent the degradation battery model better. And when you basically talk about power as a proxy, then power is multiplied like voltage multiplied with the current, and we know that voltage varies with the SOC, and then and the current is also gonna, so using power is looking like a little bit,
That's right.
so
It is less accurate, yes. But kind of the purpose of the performance models is to hand over to do an economics model, right? So they want to know how much power is going to and from the grids, and they don't want to deal with currents. It's kind of basically why we're kind of sticking to like modeling on with power. Yeah, what we want to know is how much power is being exchanged between the battery energy storage system and the grid ultimately. So we want to kind of model based on that, and so all that error kind of gets baked in. Yeah.
thanks.
All right, I think there's one more question, Ahmed, and then maybe we can close things up. Do you want to ask about the health? So what is the health parameter capacity? I guess it's for Alasdair, so.
Oh, sure, yeah. Yes. So that's our parameter. Oh, sorry, I can hear myself right now.
You're really quiet, Ahmed.
So is it, did you use capacity for the health of the battery?
It's not explicitly capacity. It is so that's a parameter that we're using for state of health of degradation is a proxy for capacity and internal resistance loss, because those affect the charge and discharge in different ways. You can take the two coefficients and compare them to figure out how much of it is due to capacity loss, for example. Yeah, I didn't go into that, but we have an equation kind of allows you to break that down into the capacity
That's fine.
component. Yeah.
So how do you calculate the coefficients of the linear parameters? If you go to the slides, then I saw there is linear equations. Yeah. How do you calculate the coefficients?
Oh, yeah. So it's just regressed versus the data, right? So we look at our previous cycles, we regress the state of, the change in state of charge versus that charge or discharge power. And then we use that to test the next cycles. Yeah.
So then you need all the previous charge discharge data, right?
That's right. Yeah.
So if you need all the previous charging discharging data, so is it physical model or it is statistical model?
It's statistics based. Yeah, it's based on time series data.
But you told most of the slides I see this is physical modeling. What does it mean?
Well, we use some physical modeling to find out what functions we should use while building a statistical model, so that it's realistic and has the physical properties that we desire, basically.
Okay. And one thing, just
go
it
ahead.
was in my mind.
Go ahead.
Yeah, I saw the results slide. Sometimes it is too much. You mentioned that the much more pessimistic, something like that. I have seen too much deviation. And for the battery, usually if we can go 85% or 80% capacity, then usually we need, this is not good to use anymore. So we need replacement. So if your deviation is that much, then even in the new battery, I need to tell them, please replace it, because you have 85% already, maybe degradation. But actually, this is error. So if you consider this way, then does it work? Do you understand the question? So the actual error I saw, that's too much deviated, right? So let's say initially it is 10% deviated, but my actual battery life is only, we can run 85%, something like that, or 80% capacity, then we need to replace it. It's not good to, or it's not safe to use anymore. So in that case, if it is not that much correct, and if it is too much pessimistic or optimistic, then does it work?
I don't think we saw that much degradation over the lifespan of these batteries, because it's only 1 or 2 years. But as what I've called focus to the trends, that if you don't take degradation into account, your battery is going to be it's going to be too bad at the start and too good at the end, because it's not taking into account that the performance becomes worse over time. Yeah, maybe because maybe you can email me. We can go into more detail. Yeah, if that's not.
Okay, thank you.
Okay, well, thanks to both of our speakers for providing some great information on the modeling and storage, and hopefully if people are interested, you can reach out. I know some of you are already working with some of our partners that are that have presented. So thanks everybody for being here. We will not have webinars over the next 2 months, because we will have theme meetings in June, and then our face-to-face meeting in July. So if you haven't registered, please make sure to register as soon as possible this week. So thanks everybody. Hope you have a great day.